That's what you've seen yesterday. Member functions, object-oriented programming, class structs, constants, references, a very interesting concept in C++, const, and there was another one at the very end. The auto, yes, the auto, that's the one. So any question about this? Nope. Well, references again. Okay, so usually in C++, when you have variables, those variables, when you manipulate them, typically they're copied. So I think it's here. Yes. So you can see my screen, all good?
Yeah, normally takes some seconds, but we cannot see the.
Yeah, it's always a good idea to double check.
No, it's okay now. Now it's.
Okay, good. So that's what you've seen yesterday about the references. That was the first slide, and then you move to the copying, because in C++, when you will assign a variable, by default you will copy it, but these copies can be at times something you don't want to have, and that's why we have references, where as soon as you are interacting with a reference variable, you are always interacting with the same instance of that variable. Even if you try to assign it to a different variable, the actual data behind the scenes is shared. So when you pass a reference to a variable, to a function, for example, any interaction with that reference variable will manipulate the data that was originally attached to the first variable. So you declare an integer, which contains the value 40, and then you pass a reference on that variable to a function. Any interaction with the referenced variable receive will modify the value 40 in the original variable. It's, if you know C, it's like pointers. Behind the scenes, it's more or less what happens semantically. You just pass a pointer on that variable to make sure that you modify the data contained in the original variable, not a copy of that variable. So that's a convenient way to do it in C++, rather than having to pass pointers like we do in C. So that's what references are. Clearer? Perfect. Any other questions? Sorry for the hypnotic effect of the recursive screen. No? Okay, we can move then to the containers, loops, and iterators. Now that you know how to declare your data and how to structure it into classes and structures, and how to manipulate it with your consts and references, we're going to see today how to learn how to have more than one of them. Somehow how to go through these containers with loops and iterators. So the slides you will see today were made by Rupert Nash. So I'm Ludovic Capelli. I'm a teaching fellow at APCC. But today I will use the slides from our colleague Rupert Nash. So the first phase will be about the containers, the first part. So you probably know already quite a few containers. Maybe you have seen in a different programming language. The containers are rather universal. Their implementations, their interactions, the syntax may change from a programming language to the next, but the actual meaning behind the scenes is the same, what an array is and all these. So we're going to see a few examples. So that you already have a bit of an idea what a container is. Somehow we have multiple times certain data. We can have multiple integers somehow being packed together. You can have dictionaries, all these maybe keywords you already know about, especially if you do, for example, Python. In the standard library in C++, you already have quite a few container classes. So now you know what classes are. So you can make classes specifically designed to deal with multiple instances of certain data, multiple integers, multiple strings. We're going to see only a few of them because there are quite a lot, especially when you start then building your own based on your specific needs. The four we're going to see today are the vectors, very used, the array, of course, then the list, and we'll also mention we'll mention the list and we'll also see the set and maps. So that should give you a rather good understanding of the different types of containers you can have. Again, the keywords may change from the way we call it a map in C++, that becomes a dictionary in Python. So the structures behind the scenes are the same and they rely on the same concepts, even if the syntax and the names may change. Okay? If you have, again, questions at any point in time, feel free to write a message or raise the hand, and hopefully I will catch that notification. So the first one we're going to see is the vector. So a vector is a rather interesting, simple maybe, but very interesting data structure where it acts as an array. Okay, you can have multiple times a given type of element, except that the size of the vector is determined at runtime. And also the fact that we're going to see in a couple of slides, you can resize it as needed. Okay, but something that is very important, because when we start thinking about data structures that we can resize when needed, is we wonder where the elements are going to end up in memory. They may end up scattered around, which is something, depending on your needs, you may not want, as it may decrease what we call the data locality, and then decrease the performance when you're trying to access things in your memory. But when it comes to vectors, the elements are what we say contiguous in memory. In other words, they are next to each other in memory, which is something which, again, for performance reasons, we really like to have. So you have a little example given underneath about how to create a vector of integers. So again, a vector, you can see it as an array which you can shrink if needed or expand if you need to add more elements to it. Don't worry about the shrink, it's done automatically behind the scenes. And then after that, you see what we're going to see at the end of this session, which is a way to iterate through the elements of a vector. So you have multiple ways to do it. And the one showed here is one way to do it. So the vectors, as it's provided by the standard library, uses all the type of interactions you're very likely to need with it. So copying and moving, accessing elements that can be at any given position, compared to other data structures we can only access elements sequentially. So you have to start with the first one, and then you can move to the second, only the third. You cannot go to the seventh element directly. With vectors, you can. Again, depending on your needs, you may need this feature or not. If you're implementing queues, for example, which is not a data structure, you don't need that access of any random element. In queues, you're only interested in iterating elements in one way or another, in one direction or another. So you can resize them. The resizing aspect of vectors is very interesting because you understand behind the scenes how much memory it tries to allocate before actually putting the data in. So there are a few algorithms behind the scenes available about how much, if you have 10 elements allocated for your vector, and now the user has filled the last 10th element, so the vector is full, and the user wants to add one more element, how do you allocate the extra data needed? Remember, all the elements must be contiguous in memory, so the extra data, the extra memory that will need to be allocated must be right after the data that is already existing. Many ways to deal with these situations. You can resize it again, as I said, when needed. Element insertion and deletion, of course. Okay, and we will actually practice this in the exercise, the element insertion. The iteration as well, you will write your own functions, you will see. Something important, the concept of ownership. So with vectors, they, what we say, own their element, meaning that at the end, the elements contained in the vectors are destroyed. So now that you've seen classes and the concept of constructor and destructor, you know what it means. If you're passing objects to it, they will be destroyed at the end when the vector goes out of scope, for example, or when you destroy the vector somehow, because the vector has ownership over the elements that it contains. Okay? That last line, I gave a hint about it actually when I said resizing. When it says resizing operations may force reallocation and copying. Why? Because if you have a vector of already allocated elements full, and you want to allocate one more, just one more, for example, data slot, one more memory for an extra element. If that element, if that location in memory happens to be already taken by another program or by another part of your program, you can't have it. Meaning that if you had 10 integers in memory and now you need 11, that location can't be used anymore. You need to find another place in your memory where you would have enough space for your 10 plus 1. So you might have to copy it. That's why, for example, if you were to I don't know, add elements one by one to a vector, but a very, very, very high number of elements, you may find that behind the scenes you have many copies, because every now and then you run out of memory in the vector you had already allocated, so you need to find another place in your RAM, in your memory, and allocate an even bigger amount of memory. But you also need at some point then to copy all the data from one memory location to the other. And all these copies might, again, decrease your performance. So the way you build vectors is very simple. Again, you're likely to have seen maybe something similar in a different programming language. The approach is the same. With vectors, we can append an element, so we can add it at the end. For vectors in C++, it's called push back. Okay, you push an element at the back of the vector. So the element you will put will be at the very end of that vector. So here you see an example of constructing a vector with all the prime numbers under the first n. Okay? Is everything making sense so far? It seems so. I don't have any. Yes, seems to be. Okay. Now the array. So the array is a simpler version of vectors because they are just contiguous as vectors. So far, so good. Their size is fixed at compile time. What does it mean? If you have an array, we are going to exclude dynamically allocated array and everything. Okay. Classic arrays in C++. When you compile your program, which you've seen yesterday when you type make, you actually compile your program, you move from the source code to the binary, that's the compilation. The size of the array you're going to use must be known then. So that means you cannot have, for example, your program asking for the user to input some value, such as, oh, how many numbers are you going to put in this array? And only then, when you're actually executing your program, allocate that array. That's a different approach. It doesn't work with arrays like that. Okay? And the second part is that, unlike vectors, you can't resize them. So if you allocated an array with 10 elements, if it's full, it's full. You can't resize it. Again, once you start doing things a bit more manually and lower level, you can do certain tricks behind the scenes. But when you're learning, you can't resize the size of an array. You can't resize an array, sorry. And yes, you can initialize them with curly braces, or curly brackets or braces. So far, so good? Behind the scenes, so the question, I think you can all see it, but just in case, Robert is asking, if I would reserve memory for a vector during initialization, would it be memory-wise or computationally wise the same as an array with the same size? I always thought arrays are more efficient. If you know you need 50 elements and you ask for a 50-element array or for a 50-element vector, which you can do directly when you ask a vector, you can directly say, prepare for 50 elements. It's the same behind the scenes. There's one call that is made to the operating system, which is, please give me a memory containing 50 times the size of an integer or the size of whatever data you want to put in it. So that is the same. Then accessing the data is the same. the time to access the data. The potential overhead with vectors come with the way you use them. So you see, for example, I said, oh, if you know you have 50 elements, you can tell the vector directly to allocate 50 elements. But let's say that you don't know how to say that to tell that to a vector, and what happens is instead you are using the default vector, which I don't know. Let's say the vector has by default 10 elements. So you fill the first 10, and then you have 40 more elements to come. So when you try to insert your 11th element, the vector realizes it's full and needs to resize. Typically, the way it's done behind the scenes is it just doubles the amount of data that is allocated. So if it had 10 elements, it will reallocate for 20. So if there's the next 10 spaces, the next 10 integers in memory that are free, it will just ask the operating system to expand its data allocated to the next 10 slots. And then you can continue to put the elements you were inserting. The overhead in this case is null. Very, very insignificant. But if the next elements in memory happen to be taken, then you need to find another place in memory containing 20 elements and copy the first 10 from your previous memory location to the new one, where you can then continue inserting. And you also need to free that memory. But that, again, is done behind the scenes by the vector. Let's say now, after you've filled the first 20 elements, you have the same problem again. And now we want to insert the 21st element, but you're out of the memory that you were already allocated. So you need somehow, again, to resize, doubling. And if you're unlucky, maybe you don't have enough space where you are to expand. So you need to find another place in memory to allocate 40, and you need to copy everything again. So in this case, for example, if you happen to time both approaches, array and vector, you might find the vector being slower. But that's why. It's not because intrinsically it was slower. It's because it was used in a way that was less knowledgeable, should I say. But that's the trick. As soon as you start to use more complex data structures, you have access to more features. But typically, there are ways these data structures are meant to be used. And containers are no exception. So that's why they're not inherently less efficient. They just have to be used maybe more carefully. All good? So that was for the array. Now the list, which you may already know. It's something we learn when we begin with algorithms. Typically, we learn about linked lists. So a list, or 4 lists in this case. Linked lists. So in case you've never heard of linked lists, they consist of elements, okay, which can be at any location in memory. They don't have to be next to each other. And each element has typically a pointer or something equivalent to a pointer pointing to the next element. So when you access an element in that list, any element, you have the value contained by this element, and then you have a pointer to go to the following, to the next element. And that's how we can iterate through it. So that's single linked list, when you can move in one direction. But sometimes it can be also useful to know how to move to the previous element. So on top of having a pointer pointing you to the next element, you can also have a pointer pointing you to the previous element. And that becomes a double linked list. So that's what we're talking about. Since linked is used when we need to, in a rather chaotic manner, we allocate them on the heap at runtime because we don't know everything at compile time. Typically, we use linked lists when we dynamically resize, insert, delete in the middle of the list, and so on. So they are extremely flexible, but your elements may end up in very arbitrary locations in your memory. So the traversal, I mentioned it, fast element insertion and deletion, yes, because you can insert or delete at any position. Except that then if you need to find a specific element, you have to iterate everything one by one. You cannot directly access the 5th element because you don't know whether that 5th element will be in memory. You will need to iterate through the first 4, jumping every time until you reach the 5th element. So that can be a bit more complex, or just not complex, a bit slower. Now the set and map. Again, very classic structures. So the set is just a list of keys. What we mean by this is a key is unique. Okay, so a set being a list of keys, all the values have to be unique. It's, again, something sometimes you may want. The map, which is something you probably know well, hash map, dictionary, all these data structures, are made of pairs between a key and a value. So it can be an identifier and some value. It can be a string and an integer. It can be an integer and an object. It can be an object and a string. It can be any type you want. Okay, it's this association. We call that associative data structure. And that's the first line here. Okay. The third point, which says you must have defined a comparison function for the key type. What that means is when you have a column which is made of the keys, okay, if it's just an integer, we understand how to find the integer corresponding to the integer you passed. Okay, we know that if you have 1 corresponds to the string hello, 2 corresponds to the string bye, and you are asking to access the element identified by 2, it's easy. But if you have a more complex map where the key is actually one of the classes that you've learned how to build yesterday, maybe it becomes a bit more complex to just ask for a specific key, because you will need to tell the map how to find an object corresponding to the object you're passing. Such as, I don't know, you're building an object for cars. So cars can have a certain number of wheels, they have a weight, they have a dimensions, and you have a whole class for this. And you're identifying records based on the car. So you pass a car and it gives you some data, okay? You will need to define a function to teach the map how to find a specific key, so a car, based on the object you pass. Maybe it will be comparing the model, comparing the year. That's something you may have to do. Ordered against unordered versions are a bit lower level based on what you want to have behind the scenes. They may use different implementations. We can be a bit faster. You can then have some assumptions. I can come back on this later if you want. Okay. So this is an example of a map. Again, I won't really go into details of this. But this, for example, you could have the identifier, the key, being the location or somehow the index of the triangle you see here in the entire simulation, in the entire mesh. Okay? And the value being either the coordinates of those triangle points and any physical property of the triangle, what the triangle is representing, maybe the weight or anything else. Okay? So here's an example of a map. So a map, remember, has key value pairs. So when you declare your map, you then pass the key, the type of the key, and the type of the value. Okay, and then you can insert into it. We're going to see how exactly. Yes, this is at the same time basic and complex. There are many containers. The actual concepts behind the scenes are rather easy. As you can see, we've gone through arrays, lists, vectors, maps, sets, in what, 20 minutes? And I think I didn't lose anyone. I'm losing the light actually. But I don't think I lost anyone because they're rather easy to understand. It's just when you need specific features that you need to go to the documentation to know if you can insert at any random location, or if you can access any random element, or checking if a certain data structure or a certain container actually contains a given value. You want to check if your map, which is something you may need later on today, if you want to check if your map contains a certain value, the way to do that might be different than a vector. If you're using a classic C array, a classic C++ array, do you even have that feature at all, or do you have to iterate through all elements yourself. This is something that can be a bit more complex because it just needs you to go and check the documentation. But again, especially nowadays, documentation has become much more friendly than it used to be, which is good. Do we have any questions on the containers? Or do we move to the loops? In the meantime, I'm just going to make sure I'm going to keep the lights on, otherwise it will just become very dark in here. Here we go. No questions on containers? Is do I speak okay, or do I speak too quickly, or in too many technical terms, or is it fine so far? How is the memory location of an array element calculated when access? Okay. So when you access an array or a vector, so contiguous containers where all elements are next to each other. Remember when I said that was actually useful for certain purposes, performance, but also other things? That's one of the other things. If it's contiguous, then you know that the location of the X element is the location of the start of your array, of your data in your array, plus X times the size of an element, X minus 1. So if you want to access the first element, then it's the start of your location, or the start of your entire array data plus 0. If you want to access the fifth element, it's the address of that first of the start plus 4 times the size of an element. So that's what we call pointer arithmetic, because a pointer is nothing else than a variable that contains an address in memory. Okay, so that's how it works. Yes. Yes, when you pass an array to a function, what you do behind the scenes actually is pass a pointer on the first element of that array. You don't see it in the syntax, but that's exactly what happens behind the scenes. For the function, in C++, the C++ array have additional features that are interesting, such as the size of the array. In C++, we don't have that. In C++, when we allocate an array of 10 elements, we just have a pointer saying, okay, your 10 elements are there in memory. That's it. It doesn't even remember how many elements there are. It just says your array starts there. So when in C we pass an array, we just pass this actual address. So you have to remember somehow that there are 10 elements there. And C++, it's also what happens behind the scenes, but in a slightly different manner. Because typically when you will create a C++ array, you will have a class called array, where you will have indeed a pointer to the data actually contained in the array, but you may also have a variable containing the size of the array. Okay, so typically you may pass. Yes. Any other questions, or we move to loops? Now that we know how to get many elements in a single container, it will be interesting to go through it. How multidimensional is array are handled? Many implementations possible. So technically, what I'm about to say cannot be the unique one, but the notion of multi-dimensional array is something that is very human, not computer. What I mean by this is your memory is a 1D array, a very long 1D array. So your computer doesn't have a notion of 2D arrays. What it does is what you visualize as a 2D array, for example. You have the first element, second, third, and so on, and then you go back to the second row, first element, second, third, and so on. In your computer's memory, you have the first row and the second row being next to each other. Okay, so you have your first row, then you have the second row, then the third row. So when you say, oh, I want to access the third element on the second row, your computer just calculates the size of a row. So it knows, for example, 10 elements per row. So it just jumps the first 10 elements So that's the start of the second row, and then it goes to the third element by doing the pointer arithmetic we just said before, which is the size of the first two elements. You jump, and then you have the third element. That's how it works. Again, technically you can have other implementations behind the scenes, but yes. Yes. With this specific standard C++ array, you can't. But we also have something, I don't know if you've seen it, or is it something you will see maybe later? Okay, no, you don't see it. Maybe managing resources. You will see how to, what we call, dynamically allocate an array. When we say this, it can't be changed at runtime, and it has to be known at compile time. We say that it's static allocation, because it's known at compile time. It's static. It doesn't move. When it's something that is known at runtime, it becomes dynamic. So we can have arrays that we allocate dynamically, where you say to the operating system at runtime, so when you're executing your application, oh, now please allocate me an array containing 50 elements. And it's only then that the operating system will say, okay, give me a second, I'll find 50 elements in memory that are free, and I will give you the address of that location. So we can do it as well. Vectors is one way to do it. Dynamically allocated arrays is another one. Remember, a vector is nothing else than an actual array behind the scenes with a nice interface to it, to append element, to prepend elements, to find the index of a given element or something. So you can use both. Follow Amir's and next questions. Do we prefer 3D array using vector container or C-like allocation? What's the best practice? Oh, okay. Do we prefer 3D array using a vector container or C-like allocation? What's the best practice? I think the notion of best practice is really dependent on the context. Depending on the field in which you work, you may have the existing practice in place being, oh, we do everything with a C approach. So we malloc, which is the way we dynamically allocate something in C. We malloc everything. Or they can use vectors. When it comes to 3D data structure, it's likely, yes, I would say it's likely to be a C-like allocation. Because, yes, typically, my experience in industry-based code is limited, but I would be surprised if vectors were used as much as raw C-like allocations when performance is important. Because typically when performance is important, we try to decrease all the interfaces around, all the potential abstract layers around our controllers. But the thing is now, if you're in a position of evaluating which approach is best, it's good because it means you have multiple approaches in your skill set. So now you can even present that to your team and then have that open for discussion based on what's currently being done and how you think things should be done or could be done. All good? Do we move to the loops? Qui ne dit consent? Okay, let's move to loops. Okay. So the loops, which again, regardless where you're coming from, if you have had any experience with any programming language, you will have seen loops somehow. In C++, we're going to see three of them: the while, the range-based, and the C-style for loop. The while loop is very intuitive, okay? While a certain condition, which is a Boolean, okay, true, false, while a certain expression holds, or certain condition holds, the code inside the block executes. Okay, very simple, very intuitive, one of the fundamental blocks of any programming language. This is an example, again, with the same prime number example. When we were pushing the prime found to the vector, we are executing it while we're still within the first n primes. Okay, so while this expression evaluates to true, the block inside the loop is executing again and again. So this condition is evaluated every time. Okay, it's not evaluated once and then you just execute forever. Every iteration you evaluate the condition, and unless of course you pass a constant, which you have to be very careful if you do that. Another approach, which is maybe less intuitive, even if actually this is becoming more and more common in like JavaScript, Python, these approaches where you iterate through a data structure, what we call with range-based for loops. So the way you can read it is for every integer x in my container data, okay, and we can manipulate x directly. In the first iteration, it will be the first element, the first integer in data. The second iteration, it will be the second integer in data, and so on. Okay, so it's very intuitive. In PHP, it's for each data as my data element. In JavaScript, it's the same. In Python, it's the same. And in C++, it's this notation. Again, the syntax varies slightly from a programming language to the next. The concept doesn't change. It's the same approach, the same meaning. And that's another element where this time you see there's this additional symbol, which now know. Oh, I just heard something. The value of the data, not the index. Joshua was asking if x were the values of the data or the index. That's the value of the data. Now, if you pass this extra ampersand symbol, ampersand, yes, you now know that you're dealing with a reference, meaning that any change you do on that variable's data is going to modify the actual variable data in the original container. You're not working with a copy, which was the case here. Here you are taking copies. Here you're manipulating the original data. So depending what you want to do with it, if you want somehow to update your container, you will need to iterate through it using references, which you now know how to do. Yes. Is there a way to cover the index in this case? Yes. Depending on the container. If you're using a raw array, there's no such feature as give me the index of that element. If you're using a vector, you have a vector set map. In C++, you will have many containers having a function called find, which will then give you a way to learn about that in the third phase today, about iterators. It's going to give you an iterator so you can find your way back. The again, depending on if it's an unordered hash, an unordered map where you have an identifier with an element. You remember key, value, pair, container. The notion index, if it's not ordered, doesn't mean anything. So you see, depending on the container you're going to iterate, you may have to find it in a different way because it will depend fundamentally on what's the data like. But you can always somehow, unless you're doing an ordered map where the concept of indexes makes sense, you can always find your way back somehow. Might have to be a bit more manual, but you can always do it. All good. It seems so. Okay. So yes, the range-based for loops, the one we've just seen here, you can do it on any container that contains the begin and end. So of course, all the standard library, STL, standard template library, have this. You can also create your own container, and if you provide those, if you satisfy those conditions, such as having a bit member function, and you can call the range-based for loop on your own container. sorry, I've not seen something. I received something. Give me a second. I'm going to stop my screen sharing just for a second. Meantime, if you have any questions, feel free to write it. Oh, it seems that my audio is becoming a bit shaky. So yes, I'm want to talk with you so that I can then save bandwidth. Okay, let's do this. I will re-enable my screen sharing. Okay, here we go. So you can do you hear me better now, hopefully? Oh, perfect. Awesome. Great. Great. So now, yes, so all the containers we've seen, so vectors and C++ arrays and the maps and the sets have that. Okay, so you can iterate through all the elements. If it's unordered, you don't know the order in which the elements will be parsed. We don't know if two elements you added to a given unordered set or unordered map will be first then the second or the second then first, because there will be no ordered enforced. But still, that's the first part. The second way to do it is with what we call a C-style for loop. So very classic that you have seen again, probably regardless where you come from. You will see this one very often, which is this time you will use indexes directly. So you will say, okay, how many elements in my container? 15 elements. Okay, so I'll take a variable which I initialize at 0. And while this variable is not 15, I will increment it and I will access the corresponding ith element in my container. So for I equals 0 until my data size, I increment I every time at the end of the iteration. So I start with I equals 0. I access data at the 0th element, so the 0th position, so the first element. In C and C++, it's 0 indexed, so the first element is square brackets 0. And you multiply that by 2 in this case. And then at the end of each iteration, you will have this code here executed. So you will increment your variable, which means in the next iteration, you will check again if it's still less than the size of the data container to make sure you're not going beyond the end, and you will access the corresponding element. So it has three parts: the declaration and initialization. You're perfectly allowed to use in this part a variable that has been declared somewhere else. Here in this example, we declare the variable inside. So that's why you see int I equals 0. But you could perfectly declare the variable I just before the for loop, and then pass I equals 0 here directly. So declaration, which is optional, and initialization in the first part. Then semicolon comes the condition, which is what you find typically in the while loop. Semicolon, and then you have the incrementation. So that at the end of every iteration, the variable you use is updated. Okay? Now comes iterators. I will go rather quickly, not quickly, but I will make sure I don't go into too much detail with this one. So if we reuse the same for loop. Any questions on the for loop, by the way? Or is everything fine? All good, okay. So the iterators, if we take the same C approach, and that's another way to do it. But the actual meaning is the same. So an iterator, try to visualize your array, let's say 1D array to keep things simple. And you can see iterators as big arrow, as big arrows above your array. So pointing to a certain element, okay? When you create a container, remember I said here that they all have begin, end, end. They all have them, vectors and so on. These are actually iterators. So they are big arrows over your data structure. So begin is the arrow that will point at the start of the first element, and end is the arrow that will point at the end of the last element. So anything between those two iterators are inside your array. Anything outside those iterators is not in your array. And then we can use it to actually iterate the array. So here we say, okay, give me an iterator. So remember, it's the same approach, different, it's a bit longer, but the structure is the same. Here we have declaration / initialization. Here we have the condition, and here we have the increment. So now let's see what happens here. We're asking for an arrow on our vector of integers. So we have a vector of integers, and we're asking for an arrow starting where the first arrow is, okay? So remember, you have begin and end, and we're asking for an arrow that starts exactly where the begin is. And you understand what we're going to do here. We're going to access the element pointed by the arrow, print the value, or in this case, multiply its value by 2. I'm going to come back on this star in a second. And then, while we haven't reached the end, we will just go to the next element. So we will just move our arrow every time by one element. Okay? And the end of our vector, we know it's when we reach the other arrow at the end, which is the end. Okay? Now we see this extra star because, yes, it seems there's something. Is data begin always returning 0? Perfect question. The timing is perfect because I'm going to answer this by explaining what the star is for. So if you ever manipulated pointers in C or C++, you know that a pointer contains the address of a variable. But if you want to access the actual value of the variable you're pointing, not the address, but if you want to get the value, you need to dereference it. So dereference, you know the references? So dereferencing is the exact opposite. It's to find where the original data is. You do that with a star. And the arrow, when they're pointing somewhere, they are actually telling you, oh, I'm the arrow that points at this element, which is at address 59 in memory. So if you want to access the actual value contained in it, you need to dereference what the arrow is pointing to. So the arrow points to address 59. So you tell the operating system, oh, please go to address 59 and give me the value contained in that element. That's what this star does. So begin doesn't give 0, it will give the address of the very first element. Okay, which might be 52,367. It's just an address in your RAM somewhere. Okay, that absolutely doesn't matter. The actual value of the address doesn't matter. It's your operating system bookkeeping job. It does this. Okay, so it just tells you, okay, the start of your data structure is here. That's it. You can, if you want, print the address. You will find interesting numbers. So that was the old-fashioned way to do it. The new way is to use auto, which you now know. Okay, so you let the compiler deduce the type for you. It's more convenient because you don't have to write this. Okay, which again is not. It's always impressive at first because there are columns, there are brackets, but it just means in the standard library, give me a vector which contains integers, and give me an arrow pointing on that container. Okay, and you will initialize it to the start arrow of this container. It's all it's saying in a C++ way. So the auto will do that deduction for you directly, which can save you time and in certain instances can also help you with performance. So again, you can implement your own container, but also your own iterator. So it becomes a bit more complex when you do that, because you need to understand how iterators work and making sure that you provide your iterator with the functions that are required for your iterator to be a valid C++ iterator. So you have here a few conditions. But if you ever want to go through the documentation and do that yourself, you perfectly can. Okay, it's actually something we do every now and then. Any questions about this? Because I think, yes, what comes next then is the exercise. Any question on anything we've seen today so far? So the containers, the loops, and the iterators. Pre-incrementation against post-incrementation. So that is an endless debate. Unless you want to go into details, they're the same. It's for performance reasons, typically pre-incrementing, so having the plus plus on the left side is better. Again, without going into too much details, but you can do both. Both are equally fine. Okay, if you have your for loop and somehow at the end you write I++ or ++I, it's going to be the same. Okay. Which again, I know is very confusing, but it's I don't want to go into too much detail already because I feel like I already covered a lot today. How does one pick the most okay. Every time I see this word, I'm very careful. Optimal data type to use from array, vector, map, vectors. Okay. So you have to know what are the assumptions that hold with your data structure. In other words, how is your data made? Is it made of a number of elements that is known at compile time and that will never change? In case an array is sufficient. Is it made of, you can of course use vectors and so on, but array is already sufficient. Is it a data that may vary dynamically? So we may start with 50 elements that is known at compile time, but at runtime we may happen every now and then to add an element, in which case you know the array doesn't support resizing, so you have to go through maybe a vector. Now, what happens if your data is not just a big array of values, but it happens to be an associative data structure, where, for example, you loaded data from a database where you have an identifier, which is, for example, an integer, and some value attached to it, such as the customer buying records, in which case you may want to use a map, because you will need this notion of key value pair. Vectors of vectors, I would strongly advise you not to do this. Let me explain why quickly, so that so that then you can have roughly half an hour for the exercises. By the way, in the meantime, if you want to start the exercises, you have I think you will have the address. In case you don't, here is the repo, which you can access. Yes. So you will find the exercise in exercises containers. Okay? Simple. I will give you also a few guidelines about it in a few seconds, because it might not be very trivial to find what you have to do, but don't worry. To come back on the question, just to finish. Yes, the vector is, okay, I will try to do this one quick. The first vector will contain elements, and each of these elements will be a vector. So that's one way to visualize a 2D array, but it's a very efficient way to do it. Why? Because let's say that your first column will be at a certain location. So you have a vector, and the first element in that vector represents a column, or row. It depends how you want to visualize it. It's the same. That column will be somewhere in memory. okay? Then the second element in the original array, in the original vector, sorry, represents the next column on the next row. But that other vector, that is now the second element, might be stored somewhere else in memory at a totally different location. In other words, not contiguous at all. And you may end up with an array being totally scattered across your memory, which is bad for data locality. Very bad for data locality. So if you know you need even like a 17-dimensional array, you can do that directly with a simple array. It just depends on whether it's going to shrink, to change, is it associative? That's all you need to do. That's all you need to know, sorry. And then based on this, you pick the corresponding structure. Make sense? I would think so. In the meantime, did you all access the exercise? Can you all access the GitHub repo? Everything's fine? No problem here? I guess it's fine. So you can find the containers exercise here, okay, with the PDF or the markdown, depending on the one you want, containing the instructions. So you will have to do 3 main things. So that's the PDF you can all access. So again, you can run this on your own laptop. If there are some of you being on M1 MacBooks, for example, using M1 architecture, you might have some problems. So we're going to see how to fix this. But otherwise, you're going to be provided with a very simple code, which you can find vector CPP and vector HPP. So these, okay, very simple source codes, extremely short. One function provided so far with another one to define. Just like yesterday, you will have the test CPP. Okay, so this file here that's going to test whether you implemented what you're expected to implement, and you have to actually implement things in this file. Okay, so that's if we have this example together. I'm still sharing my screen, right? Yes. So in this example, you have a function that takes a vector of integers, okay, a constant reference on it, meaning you're not going to modify that vector. And what you want is, in this source vector here, to extract all the elements that are even numbers, create another vector from it containing all these even numbers, and return that vector you just created. Okay? So that's the first part. So try to do it. And in, I guess, 5 minutes, we can correct it. In the meantime, if you have any questions, as always, feel free to ask. How should I proceed? Should I do the same with you? Yeah, just to be sure, 5 minutes is just for the first function, okay, not the entire exercise. Don't worry, we'll have until 11 a.m. for the entire exercise. This is just for the first function, yes. Yes, thanks Juan for asking for clarification, because what maybe a bit confusing.
No worries. Thanks for clarifying that.
Now the thing is, I expect something which is, oh, okay. Is the C++ function for powers pow e? Yes, that's okay. That's a very interesting. Just to be sure, to check if a number is even, so a multiple of 2, all you need to do is this, okay? It's, in case it may help. It may help. That's how you check if a function is a multiple of 2, so even. But yeah, power is the function that that calculates powers. Yes, you copy them and you push them in the new vector. The more challenging part is that typically you can't compile your program. Well, you can compile it. Let me double check something. Because of the test, the way it's designed with the test is that the test won't run until you have everything done. Juan, which approach do you think is better? Providing them with a main CPP file that just runs their function, or because the thing with the test CPP file is that until you implement everything, well, you can still have it. Let me check.
I will do a quick test. Whatever you find it easier, up to you. I will just I will not maybe not bother that much. So I mean, just check if it's working. Maybe at the end, if the exercise is finished, you can do more testing. But yeah, that's not.
Okay, so it's been 5 minutes, so I believe we can go through it. So let me delete my my existing code up so that I don't start with a solution already done. Would be a bit unfair. Okay. So I'm going now to share my screen again. Show application screen, share screen, this screen. Okay. So for the first exercise, this one was probably easy. So first, can you all see my screen? Yeah, I believe it's fine. Yeah, I think everything's fine. Yes, okay, perfect. So since we are going to return a vector of integers, the first thing we have to do is to declare a vector of integers that we're going to return eventually. So only even numbers. Okay, and I will return that. Only even numbers. Now the hard work is what goes in between. So somehow I'm going to have to iterate through my source vector here and extract the numbers that are even. So somehow I'm going to have a for loop doing something. So the easiest one, or the most intuitive, is probably to say for every integer that I will call x in my source vector, then I will do something with x. So if X has some properties, typically even, then I will add X to my vector here on the even numbers. And we've learned how to add a new element to a vector is by using pushback. Okay. You may have in your example source having a lowercase s, so make sure you keep that in mind. By reflex, I just renamed my with a capital S, but it doesn't change anything. You just have to keep the lowercase s. So you declare a new vector in which you put all the new numbers that are going to be even, and you iterate the numbers in the source vector passed. You check if they're even, and if they are, you push them in the only even numbers vector. Easy? Well, if this was fine, then you can move to the second one, which is a bit trickier, which is in the vector HPP file, you have another function, this one, which is declared. So you have it in the HPP file, but it's not implemented, it's not defined, and you need to define it. So the starting point to define it is to copy that line, okay, print vector of int, put that in your CPP file. Not this one, this one. Yeah. So remove the semicolon and just add braces, okay? So that's your starting point. Again, once you have this, then what you need to do is, so this one is a bit tricky. I want the tests are designed so that what you print must look like this. Sorry. Okay, so you must print a square bracket, and then every time it's a space with the number that you're reading from that vector of numbers. And then every time there's a new one, it's comma, space, number. I say this because the tests, if a space is missing somewhere, for example, the tests will say that it's incorrect. Okay, so this one is likely to take you a bit more time. Let's go again with 5 minutes. But I'll try to do it at the same time very slowly. So if you don't want to hear me, you can just like decrease the sound on your laptop or something. Don't try to mute me, otherwise when I'll say okay, we can move on, you won't hear me. But you can always decrease the volume if you. So for those who want a bit more hints and want to code with me live, so the first part we're going to need we don't even need a string, we can output directly. So how do we output? We output using the two symbols less than, okay? And we begin with the square bracket, and up, we just pass the square bracket, okay? Then somehow we're going to have some iteration over the data, so we know how to do that. Again, okay? Many approaches, as I've shown you, you can do while, you can do a C range, you can do a range-based for loop, you can do a C-style for loop. Many approaches. The one I'm using here is the same I used in the previous exercise, okay? Which will be to just iterate through this, what I find rather intuitive way. So for each integer that I will call x, in my vector data, okay, I print a space and I print the integer, okay? Now we'll probably have to do some tweaking at the end to get the spaces right at the right position. So what I'm missing for now is the comma. So the thing is, I will always print a comma at the beginning of that line, except if it's the very first iteration, because here the first time we don't have a comma. So the first time I just want to print the space and then the number, but all the times after that I want to print a comma and then space and the number. Okay, so all I need to do for this is to have a boolean somewhere, for example here, that says, oh, this is the first iteration. Okay, so I will use this variable for this purpose. So I will have a boolean is first. You can use an integer, you can use everything you want. And I will say, okay, if it's the first iteration, then I don't print the comma. I will just say, okay, it's no longer the first iteration. Okay? Is it okay so far, what I've been doing so far? The trick here in this exercise, yeah, it's not really to iterate through the container, it's just to get the printing format right. So if it's not the first element, then we know we have to print this extra colon. So we just print the extra colon, and at the end we just make sure we print also the corresponding closing bracket. Okay, and that looks good to me. So for every integer in the vector here, a vector containing integers, I iterate through that vector using that approach here, and for each element I output this element after a space, and I add an extra comma if it's not the first element. Okay, does it make sense to everybody? Even the ones of you who decrease the volume, does what you see on my screen make sense? Yes, okay, perfect. So now comes the last exercise, which is a bit tricky because you should have been given maybe slightly more guidance. So for the last exercise, which you can find again in the PDF, or you can even find in the slides here, it requires you to write a new function, this time for a map. So the thing is, you're going to create a function where it takes a map as an input parameter. Or am I not sharing my screen anymore? Yeah. Why are we using std stream output and not simply stream out to std out? Because std out, oh yeah, that's okay. Std out is the default output stream. But let's say that you may want to have your function able to adapt to any output stream. It could be to a console, it could be to a different device. If you're an embedded system, for example, in embedded systems, for example, you may have, okay, that's the output stream I want you to put the data on. Don't put it to the default one, which might be the console. Put it to this, where behind the scenes it's redirected over the internet or something. So that's why we use the one we receive and we don't hard code everything to stdc out, even if for this specific exercise, we know that we just want to output it to the console anyway. But let's say it's just good practice. Now the last one is a bit trickier, yes, because you have to create a file called mapx.cpp, okay, map exercise. So mapx.cpp and maxx.hpp. I'm going to show you the HPP version, and you need to create that function here, which is what the text, or what the test file will expect. So you can directly copy that. Actually, I'm going to copy this in the chat. It will make your life easier. So you create a file called mapx.hpp, okay? And in this, actually, I'm just going to give you all the lines directly. Include vector, then we have the map, then we have the string. Actually, we don't even need the vector anymore, but it's fine. Up. That's a bit old school, having to copy paste, but that's fine, it does the job. Okay. So that's your starting point. You have a file, mapx.hpp, where you have that code, only 4 lines of code after all. And how it works is, for this function, it will take a string as the key, as you can see here. Maybe I will show on my screen here. The key is the first part, so it's a string, and the value is an integer, because this map contains words or strings as their key and the corresponding string length as the value. So if I pass hello, it will store hello as the key and 5 as the length, because hello has 5 letters. Okay, simple. But you need to implement it. And there's another trick, which is if the value already exists in the keys, so if you try to insert the value, the key hello twice, then it should return false. So if it's the first time you insert a value, you actually insert it in the map and then you return true. If it's not the first time, you just return false and you don't do anything else. Okay? Does it make sense? I guess everybody is already working on their implementation, that's why. You may want to use, since we are using map, you may want to use find, because we're running out of time a bit, so I don't want you to spend too much time online trying to find something. This function here, find, that's one of the advantages of using maps, is that you have these features for you. Lookup feature in this case. So find will return an iterator on the element found. Remember iterators, these arrows that you have above your array? The thing is, if it doesn't find an element, it will return the arrow at the very end of your map. Remember the arrow that is at the end of the last element, so which represents the end of your data? That's exactly it. So my map end, which is something we have seen in the slides, used for iteration purposes, is the iterator that will be returned if this value here is not found. Oh, I'm no longer showing my screen. Silly me. Oops, sorry for this. So you have in the chat everything anyway. So this iterator here will be returned if that some value is not found in my map. Okay? So that's how you can check if the value is already in there or not. So let's try quickly then to correct this. So I'll show my screen again. So the approach here, I'll just use this one as well. Source insert. That's it. Here I need string. My string is name, and here I need the length name. Okay, we can do this one. Okay, so what this function does here is first we try to check if we already have that name in our map. Okay? If it tells us that it didn't find it, then we return false directly. Okay? If it hasn't found it, then it means it's a new element, so we insert it. So how do we insert? You can find online documentation about this to go in more details. But you just call directly insert and you create a pair. So a tuple, let's say a pair made of a string, which will be the identifier, the key, and an integer, which will be the value, in our case the length of the string used as an identifier. And that pair, the actual value in that pair will be the first part for the string, the actual name that we pass, okay? And the value will be the length of that name, or the length of however you call that variable. And since you successfully inserted an element because it was the first time, you return true. Okay? Does it compile? Did I miss something somewhere? Like a silly typo somewhere? Oh, yeah, okay. Well, if you have something like that in this case, well, I can fix it. It's just going to make the code a bit harder to read because I will need to change a few tricks in there. That's fine. A test failed because when it's empty, I should not have a space here. You see, for the, which one was it? Test CPP. Oh, it doesn't indicate which one it is. It's for this print. It's for the print. For the print function, typically. Is there any question on the map? Sorry, so I want to check the vector, but is there any question on the map, which is the important one? Or is it fine? Because we are now at 11 AM, so I think it's going to be time for you to enjoy some break before the next session. So I want to check if you have any last-minute question before we finish. All clear? Great. Anyone else? All good? It seems so. This is not a build with G++11. I would need to check why it doesn't build, but yes. Okay, well, great. Then I have to free the room because there's another meeting in it. But if you have any questions, of course, feel free to ask. I will have a look later. And great, thank you for your time, and have a good day. Enjoy your next session. You will find the solutions online. Don't worry. You have all the solutions available online on the GitHub. So if you have any questions, they will be fixed. Great. Thank you for your time. Have a good day.
Okay, so I think that yeah, you can see the slide. What I will talk during this part of the course is about resource management, and we will talk more about pointers. This part is a little bit because there are many new concepts regarding memory allocation. Please, if you have any during the lesson, if you have any questions or anything, please let me know, and I will try to explain things like slowly or better. I will try to because the idea of that is to understand better how we can manage resources. We will focus here more in memory. Okay, so when we talk about resources, we talk about, for instance, memory. If we may need to allocate a vector of some integers, or this vector could be like very large, and we will need to handle that. We can also handle files, to open a file, read the contents, then close the file. We're talking also about GPUs, network sockets, that you can open a socket and listen to that socket, and then close this listening. Another example is about databases. When you use a database, you need to connect to this database, perform a query, then you need remember to close this connection. So there are different types of resources that in C++ or any other programming language we will need to handle. Here we will focus more about on memory. So when we run a program in our the operating system is the one that is that manages the memory and provide us with a chunk of memory for that program. You will see in the graph that there are some part of that memory that we get is for the instructions, the program instructions, and also another part is for the data. And the data is saved in the stack and also saving to the heap. We will see the differences of that. So it's mentioned that we normally, when we talk about an address, I think we mentioned a little bit about that yesterday. We talk about in the memory where is located that part of information. So we will see when we print that. Normally we use hexadecimal numbers in order to get a memory reference. So as I mentioned, we have two. We have a stack and we have the heap. So we will see the differences of that. So we will talk about C++ and also this is similar to C as well and other compiling languages. We use the stack to store local variables. What that means is when you write a program, when you define the variables that we want to use, and for instance, if we have it's called a static vector, that means a vector that we already know the size, so we can specify that in the source code. All of these elements are saved in the stack because the stack is close to the because it is close to the where the instructions are located in memory, and normally also the size of the stack is fixed. Normally it's faster to get access to the variables that are saved in the stack. So a recommendation is, for instance, if you are using a small vector for some, you know beforehand the size of that vector, the recommendation is to use the stack. Drawback of the stack that is not mentioned, that normally is not that as big as the heap. What that means, imagine that you need to open or to save in memory for some reason a long vector or a picture that is quite big. If you use the stack because you already know the, let's see, the size, it could be that you don't have enough space in the stack. So in that case, you would need to use the heap and allocate the memory dynamically, is called. So let's say that everything that is allocated statically, so it's like, let's say, breathing in the source code is saved into the stack. Let me check if I'm forgetting something. Well, there is a mention that in C++ written that we call a function, we change the stack pointer that this is called, that is where all the local variables are saved, change and moves one position increment and moves this stack pointer in order to and we get like local variables that the scope is from this function. We will see a little bit about that later. And also, when you finish the function and you return, the stack pointer is updated and the allocation, the allocation has no cost. That's why using the stack is faster than that, because it's what you are moving when you call a function, and when the function returns is only a pointer. It's called the stack pointer. Well, it's mentioned that it's static because these variables are allocated at compile time, not at runtime. Okay, so this is regarding the stack. And regarding heap, this is when we use dynamic allocation. So if, for instance, let's say that the software is to handle pictures or to process some files, beforehand, we don't know the size of the picture, of the size of these files. Or it could be a vector that for some reason we don't know the size. In those cases, we need to allocate the memory dynamically because we don't know beforehand the size. Yesterday was mentioned that would be like this is like done using a new delete. I have seen in the documentation that this is called like a low-level memory management because this lesson we will see other ways of handling this memory dynamically. In C++, let's see, the low-level functions are new, delete. If you use C, you will use malloc or free. There are other versions of malloc that you can book a vector rather than a chunk of memory that I think is called calloc. And for instance, if you use Fortran is allocate, deallocate, but this is when you use the heap and you use dynamic memory. Normally, you cannot rely that much on the heap. I mean, in terms of if you do a lot of allocations in the heap, the memory could be fragmented and the access could be slower than the stack. So my recommendation is, again, if you know for sure the size of a vector, or you know the variables that you will use, specify that in the source code, and in compile time, this will be defined, and when you run the program for the first time, the memory will be already allocated for you. Because if you do it, I mean, for some, there are a lot of cases that you don't know beforehand the size. And of course, you can use the heap. But when you submit a request, is the OS the responsible of finding a chunk of memory in order to give you that access. Hopefully that makes sense. And also, when you finish, you can free that chunk of memory that you have allocated. Otherwise, if the software could, if you do a lot of requests, you can take a large amount of memory, and you will slow down a little bit the execution. Okay, let's talk about the pointers in C++. This is let's say like a kind of, this is called row pointers in C++, and also this code is pretty similar to C. The only part that is changed is to print that in the terminal that we use cout. In C we will use printf or other functions, similar functions. So the important things here, I don't know if I can. Okay, yeah, I see that. Here in this line we define an integer, and we initialize with value 99. And here what I define with int star is a pointer. So this is a pointer to this integer. When we initialize this pointer, what we do is the variable I, we will get the address. To get the address of a variable, we use the ampersand. And what it returns is the address in memory where this variable is located. So here we have this pointer. And now if I need also, well, it's not covered here, but also we can, that is called like a pointer arithmetics, that you can use the pointer to, imagine that you have a vector, you can use this pointer to get access to all the elements of this vector. But in this example, what we are doing is we want to increment the value of I is 99. So we will make it, let's say, 100. So you can do E plus equal 1. So that will be handling the variable. But in case that you want to use the pointer, when you use the star, you say, okay, this is the pointer. I want to modify what the position of memory that is pointed to. So if when we use that, we get access to the variable I. So we get access to 99. And here what I'm doing is I'm incrementing that value by 1. Does it make sense? This is like a, let's say, also this is in case that for some reason you need to use a C, this is the same for C and C++. This could be at the beginning a little bit confusing, but you will see that with practice you will get more, let's say, efficient, or you will remember that. Also, we are talking about pointers. Yeah, there is a comment in the chat that is, okay, let's go to the previous slide, that I is the same as star I PTR. Exactly, yeah, it's the same. So you can, here in this line, you can use either I, but imagine that for some reason you get the vector, sorry, the vector. you get the pointer, you can modify the region of memory that is pointed to. So this pointer is pointing to the value of I, so you can modify that. So that makes sense. Why pointers also are useful? For instance, when you call a function, let's say that you have a large variable or a large vector. If you send the vector by reference to the function, it's more efficient to use a pointer rather than sending the whole vector. Because in that case, when you call a function, this you will not need to copy the contents of the vector, and you can have a reference to that pointer. So what it said here that you remember in the previous slide we have defined a pointer, and we gave a valid address. So we said, okay, the variable I give me the address. Fair enough. But we can also define, you see here that we use the format is normally for addresses are hexadecimal. We use here a random memory address. This is well, dangerous. This is, let's say that we don't know how this when we run the software, we don't know how this will behave, because if this address, if there is inside or let's see the chunk of memory that our program has, it could modify positions that we don't want. For instance, it could modify some variables that we don't want to modify them, or even could modify some set of instructions, or this memory address could point to a variable that is from another program. This is very likely that when we run this software, it will crash, because also the one function of the operating system is to check that, let's say that you are behaving well and you're using your memory space. In case that it detects that you want to access somewhere else that you shouldn't access, it will kill the process. But this is typically a crash, or there's a silent corruption of data. Imagine that this address for some reason is we're lucky and is valid and is inside our memory space. We can modify positions that are not that we shouldn't modify. So this is also a sample that we should be careful with the pointers, and also keep an eye that, for instance, in the first case, we are using them properly. We have a variable, so we get the address, and fine. Also, we are talking here about this. We were talking before about the scope, that we have the stack pointer, and every time that we call a function, the stack pointer moves and then returns. This is because, for instance, we have here an integer I equal 42. This integer, the scope is this one, is defined by these curly braces. At the moment that they finish this function, this position of memory will be released. We will not have any control of that. So if I'm returning the memory address of this position of memory that will be released when this function finishes, we will have a memory address that, yeah, could contain 42. But if we call other functions, this position could be reused. So it's completely we don't know the behavior that we will get. So again, as they said, that returning a pointer to a local variable is a recipe for problems. So be careful with that. Normally, what you will do there, maybe, yeah, it could make sense, for instance, when you allocate something and this allocation will continue in time. But yeah, you should be careful with that because you are giving a memory address that is no longer valid once that it returns. So it's also here is explained that when you you define a class, and a class could contain several pieces of data. If for some reason you need to allocate dynamically a vector, you need to, when you call the class with the constructor, you will allocate that vector, but also you will need to remember to free that space when you finish with this object. Well, I don't know if has been mentioned the difference between class and object. Do you know what the difference is when we're talking about class and we are talking about objects in object-oriented programming? Well, just to make, when we're talking about a class is, let's say, the definition. So it's like okay, a class will go exactly in the. I see in the chat that it's mentioned that the object is an instance of a class. So let's say the class is kind of well, templates are also used in C++. So yeah, it's like a kind of like a skeleton definition. The definition that you say that we can have some instances that will contain this data, this data, this data, etc. When we talk about objects, are like this is called like more is a instance, like a physical. Yeah, well, this redundancy, but physical objects that you have in memory, and they contain values. So when you create an object, you will allocate some memory, and when you for some reason you don't need any longer this object, and when this object is out of scope, this object is released. But if inside this object, if you have allocated some memory, when you finish, when the lifetime of the object finish, you need to release the memory in order to also have enough space for future allocations. So for if you're using ARCHER2, your laptop, etc., to make more memory available. Well, this is what is explained here, that if something is allocated in the object, when the object finish, it's called a destructor is called. When this happens, that object reach the end of their timeline, when says a local variable goes out of scope, for some reason, when you delete this object with the function delete, here is mentioned that you should never call the destructor directly. Normally, what you do is you create the object, and if you want to delete the object to free space, you call delete. You will never call the destructor. Here, this is C++ has several patterns, and let's say several procedures, let's say, and the one that is explained here is resource allocation is instantiation, or resource as seen on the internet, that is also mentioned like is resource acquisition is instantiation. What that means is when we create an object, the constructor should book the memory that will be needed for that object. Or let's say that we are talking about files, an object that handle a file. So when you call the constructor, when the object is created, you should open the file. And when the object is destroyed, you should close that file. It's the same, for instance, for a database. When you create the object, you perform the connection to this database, and when you get rid of delete, destroy the object, you should close this database connection before destroying or deleting this object. If let's say that this is done manually for some reason, you are not following this pattern. So the idea is to make let's say the class of class object to handle these resources and not give that chance to the developer or the user to do this handling, to let's say to make this resource allocation or resource handling transparent to the user. And what is said here, that when the compiler destroys your object, it will release the resource. So this, if you follow this pattern, this will be done like behind the scenes. You will not see any of that. Here we have an example of we are defining a class that is called myArray, and this class has two pieces of data. We store the size of the array, and also we store a pointer where we will save the data. The pointer will contain data that will contain a chunk of double precision floating point numbers. You see that this is initialized, size is equals 0, and data we also initialize null to a null pointer. Null pointer also is the address 0. So normally the address 0, there is nothing there. So we use this null pointer in order to check if, let's say, the address is valid or not, or has been initialized or not. And there, when we move to public, we have the constructors are public. So we have the empty one, that is my array, that is equal default. That means that size will be 0 and data will be a null pointer. And then the next constructor, you can call it when you created the object. And this constructor you will need to specify the size of the array. I've been talking a lot of time because you can use the array of a vector. It depends. I don't know. Some people prefer to use a concept of array. Some people prefer to use a vector. I'm noticing that previously I've been using vector, but yeah, I'm now using array, but yeah, it's the same. So when I define my array, I will need the size, that this is n. And then you see that the size is defined here. So we define we use the value of n and we store it in the size. And for data, what we do is we will allocate using new. We will allocate a vector of the doubles and the size will be size. And also notice here that So notice here that I define the destructor. Why? Because when I use the constructor, I book some memory using new. So when this object for some reason gets destroyed, you will need to specify. You will need to also free that memory that you have allocated. So this is called delete. And this piece of code follows this paradigm, well, this pattern that we have said before, that is resource allocation instantiation, because this is done, let's say, behind the scenes. When you create an object, the memory is allocated, and when you destroy the object, the memory of the vector is free. And also here we define the operator square bracket, and we return the data that is in the square bracket. I see that there is a question in the chat saying what is the meaning of explicit here. That means we can see later an example that this constructor can only be used if you call it in an explicit way. Because sometimes if when you create an object, if you call the constructor not in, let's say, not in that way, the program itself, the compiler can guess, okay, I will use this constructor because it seems that this is closer to the what I have defined. Let me show you an example. That is explain better this concept here. So with explicit, you tell the compiler that you shouldn't use this constructor in an implicit way. So this is what you need to remember. And the sample is here. I will let's see if so I will copy in the chat this website. So you see that, for instance, you have two classes. You have the struct A and struct B. So in struct B, you use explicit. So for instance, when you use that, use this part in A, select the first constructor, but because in B you have specified that this should be called in an explicit way, when you use that, it fails. So this is the explanation of how that makes sense. Okay, so I have that. I will now what I will do is I will share my. Let's see if I can. I will use one example that is in the documentation. Have this prepared. Just one moment, because I need to go to the repository view, lectures. I will copy in the chat. I will use the samples that are there. And I will do is I will share my this tab. So here what I'm using is I'm using an online compiler. And the code that I have is in order to make this like a more interactive, you see that this is the same code that we have used before. The file is called r1.cpp. I will paste that in the chat. And you see that, yeah, I have class my array, I have public, these two. We see that here we haven't specified explicit, but well, so like so it depends to the programmer, and here what we have is some debugging, like messages. So when we perform the construction, we print data. That data is the pointer, and when we destroy or delete when the destructor is called, we also print a message. So if I execute that, I can here clicking compile, link, and run. Let's see if what is the output. You see that well, the first one is called, we are creating two variables. We are creating a variable called null and a variable called x. So I have a my in the same in the first case I call this first constructor, and in the second case I call this second constructor, and I allocating some memory, and I start constructing, and here you see that I have a memory address, and this is there will be 10 positions for double floating point numbers, just for this case. And when this program finishes, you see that there is this brackets, this curly brackets, this curly braces here. The object gets destroyed. So you see here that is destroying. So destroy this object that is calling this x, and then destroy this object that is in null, because you see that we have defined a null pointer. So it's that is destroying 0. Also, when you call delete, if the delete detects that the pointer is 0, doesn't do anything, because it means that has not been is not anything allocated there. Also, there is here that I use delete and square brackets, because there are two deletes. When you allocate a variable, you don't need to use the square brackets, but in case that you delete a vector, you are saying that you are freeing more than one position of memory, or one. I mean, that could be either one or more than one. So you are specifying that with the square brackets. Also, there is another. So if I modify and I use auto y equals x, what I'm doing is I'm creating a new variable, and this what we are doing is I copy the content of x in y. So what happens if I execute this software or this piece of code? Let's compile, link, and run. I get an error here. I get, you see in this case, sometimes the errors are not like quite, let's say, explicit, but in this case, I got an error because it's the double free or corruption. What that means? That when the program finishes, it goes backwards. So it tries to free y, then try to free x, and then tries to free null. So I am free y, so I get you see the destroying this memory, or let's say releasing this memory position. But when I get rid of x again, I free this position. So that's why when if you free or you delete twice the same memory address, you get this error. And this is because I will start sharing. We need to specify, we have a specify constructors, we have a specify the destructors, but also if we do copies, we need to specify a copy constructor and a copy assignment operator. What that copy constructor is when you create a new object as the destination. So that means you see here that I define my array. I define x 10, fine. I define this y, fine. But here you see that I'm defining my array set that is equal to x. So I'm creating a copy of. This is called a copy constructor. And copy assignment means that when you have here you define x, is my array, but here I'm giving a new value to x. So I'm assigning a new value to an existing object. So in that case, I will need to free this allocation, and and this will be like allocated to x. This is, here is said that, for instance, if we don't need to book to allocate any memory, the compiler itself does that. But if what is happening in the example that we have shown before is that we are doing this because what the elements here in the class is you see this is a unsigned integer, and this is a memory address. So what it does, yes, manage and copy both the address and the size, but we don't want to do that. We want to manage the memory that points to that address. So let's see that the compiler is not that say intelligent, or we haven't give the compiler enough hints to do that. So if we want to copy array, we have to either copy the data, that this is called a deep copy, or do a shallow copy, that is copy the pointer, but also use other types of pointers that keep track of the data that is pointed to. So here in this piece of code, there are two new functions here. The first one is when we is this part, that is when we create an array from another array. So what I do is I do a copy of the data. So I copy size, other size, and the data. What I do is I create a new vector or array with the size, and then I copy the data manually. You may think that, for instance, you can use a for loop to copy the data, but there is a more efficient way, that is using a std copy. So you copy the chunk of memory rather than copying the element one by one. And the second part is here, that what you do is you are, let's say, getting rid of the previous object and creating a new one. So what you will need is to free the data that has been already allocated and book the new data and copy that data. So the first function we will call when this is executed, and the second one will be called when this part is executed. You see the difference? Because here set doesn't contain anything and you are doing a copy of X. But the thing in this case that the X contains already an object. So what you are doing is you are assigning another object. So the previous one, if you don't handle that, it will occupy memory that you cannot have access any longer. Also, it's mentioned here that when we return, when we use a function and we return the value, may think that this is copied to the target, but well, actually, yeah, this is the sample that we have a function called read data that you define the answer that is a vector, so you allocate memory for that vector, read, etc., and then you return this vector. The thing is that when you return the vector, you return a copy of that you return ARCHER that this is a copy of this vector. So this will create a copy, and you will need in this, like, let's say, simple chunk of code, you will do two allocations. The first allocation is here when you define this vector, and the second allocation is done when you copy, when the result of this function is copied here. So this is like a, let's say, a double, like a bit expensive, let's say. So one concept of that C++ have is the concept of move. That is well from C++ 11. When this is used, when they said the sample is automatic variables that are going out of scope. So when a variable going out of scope, rather than this vector be copied to this and do like another allocation, etc. Let's say the chunk of memory that has been already booked, rather than get answer pointing to data, because answer is let's say delete, data will be pointed to that chunk of memory instead. So there's here that is like you kind of steal the container resources and are in a undefined state. And also, it's important that when we define our class, also we should to take care of this on defining these two moving functions. So you see that here you use swap, and you copy your let's say size of data, you copy to other. So when you return an object of this class, do a move of moves or change ownership of the data, rather than do a copy. And the first one is the other side. the first one. And also, what you may wonder why we use no except. That means that these constructors will never launch a exception. This is a condition when we use the containers that we have seen in the previous lesson. Needed that in order to move data, needed that condition. If this condition is not met, if we don't specify this keyword, the data will be copied rather than moved. So that's why we are specifying this no accept here. There's another feature of C++ that we can throw exceptions. I don't know if you have seen Java, C#, also they have these exceptions. So we are talking now the rule of 5, that the rule of 5 says that if you define or delete one of the following, you should probably do so for all of 5. So let's say that this is when we are talking when we define a class and we handle resources, that in this case is memory. Again, could be a file, could be a database connection, could be a socket. So if you define one, it's very likely that you will need to define all of these 5. Copy constructor, copy assignment operator, move constructor, move assignment operator, and the destructor. On the other hand, we have the rule of 0. That means that if you are not working with any resource, let's say if you don't need to book memory, you don't need to open a file, you don't need to open a socket or listen to a socket, open a database connection or connect to a database, let's say, you don't need to to use these functions. It's like a kind of like a more like a simplistic view of. Here, what is explained, I see that it's like we are like getting close to the finish there, so I will try to summarize this, and if you have any questions, we can solve them. You can either use the share pad, or I will do in the chat. I share the share pad in case that this afternoon or later today you have any questions. Please paste them there, and I will answer them later today or tomorrow. Before we were talking about pointers, and I said that these were row pointers. Row pointers because let's say that we have a full control. We decide when we when we allocate some memory, destroy, etc. But C++, I think it's from C++ 11, contains some it's called some intelligent pointers. So one of them is a unique, the unique pointer. That this is a pointer that uniquely owns the object it points to. So the object can be, let's say, it's like you have an object, and this object is only referenced by one pointer. So if you declare another pointer and you point to this object, this object will never be copied, will be moved instead. So you see that there is no these two copy constructors will be delete. There is an example here where you can use the way of using a unique pointer is you return, you use it here. Well, you define the pointer, so you have std unique ptr, But what you do is you return std make unique. So this pointer will be a unique pointer. Here is this class is expanded. You have x and y, and well, you see that you can have here you can create a image like let's see a variable. To create this variable, you get the contents of this pointed with this pointer, and then you can work with the image ref.x. So in order to, you have seen that in order to access these functions or methods, you can use the dot point. You don't need to specify that, and you can work with the pointer. So you can you use the pointer, you get the position of memory that is pointed to, that is an object of an image, and you can call it with .x. You may have seen in C++, and also this comes from C, that you can use the arrow. So this syntax and this one is similar. Here what you said that is that you have a pointer, and using that is like you are using this method that is contained in the object that is pointed by this one. I would say that this is more readable than this one, but you can use both. This is also because in C and C++, you normally use like a quite, you may use a lot of shortcuts, and you can write like a long code. You can write it like a very summarized, but I understand that sometimes it's not that perfect for readability. Also here we have the concept of I'm finishing the share pointer. This is that for some reason you want to have an object, and you want to use this. You want to have several pointers to that object. You can use this share pointer. So this is the idea of that is like when you have several pointers to this object, the object is not destroyed, but when the count of pointers that is pointing to this object is 0, the object is destroyed. That's why it's called an intelligent pointer, because it can manage the memory for us. There is a note there that is prefer unique pointers unless that you need to share. What else? Two things to bear in mind with the share pointers. For some reason, we would want to get a pointer to the class itself. So to do that, you will need to, when you define the class, you will need to specify this. std enables share from this, and you can return a pointer to your share, to the class or to the object itself, using this function, share from this. Also, another thing that these share pointers are no longer, because you can define the two share pointers. Here you have defined this class called cowboy, so sample, and you have this PTR and partner, and the thing is you partner up these two in main. You have two objects, good and bad, and you partner up, and because this partner pointer is pointed to the object bad, and the object bad has a pointer that is pointed to the object good, these share pointers are pointed like one another, and when you finish the execution, or when these objects good or bad are out of scope, they will not be freed because that is already they have a point. They're, let's say, pointing each other. So this is also another thing that you should bear in mind. Well, I mentioned before about row pointers, that you can use these intelligent pointers, a unique PTR or a shared PTR, in case that you want to give the compiler the opportunity to handle these objects in memory, but also you can use row pointers that could be also valid. It's not a big deal. We're talking before about other resources that could be files, database connections, sockets, etc. That again is if we use this concept of resource allocation, instantiation, I don't remember now, the RAII. Again, this is like a handle behind the scenes. You see that the constructor opens the file with the std open, but when the class, the object is destroyed, you see that, well, if handle, because null pointer is a 0. And also in C and C++, the conditions, you can compare numbers. It's true if the number is not 0. So if the number is not 0, means that the handler contains a memory reference. So in that case, you close, well, it's a memory reference, but it's like a pointer to the file, let's say. You have closed this file handle is called here. Exercise related to this one is exercise Morton order. You can have a look this afternoon, and again, any questions, please put them in the share pad, or if not, we can solve them tomorrow morning. Tomorrow morning we start at 9:30. I think I can join I will join at the beginning of the session in case that you have any questions regarding this part. Sorry that, yeah, I'm again 5 minutes late according to the schedule, but not sure if you have any questions now. This part, to be honest, this part is quite complicated to to understand. It takes some time. For instance, in my case, personally, I'm more familiar because I'm more familiar with the C and let's say like a previous version of C++. So I work a lot with the row pointers and yeah, know a little bit about the pointer arithmetic. But this concept of a unique PTR, shared PTR, and also when you declare a class, that you need to take care about the constructors, the destructors, copy assignment, copy move, all of this stuff is a little bit complicated. There is a question in the chat, could you talk through the solutions to the exercise in the session tomorrow morning? Yes. So tomorrow morning we will start with this exercise, and then we will continue with the lesson and with the course. So yeah, I will talk through the solution to the exercise tomorrow morning. Any other questions? If not, thanks a lot. And yes, let's see you tomorrow, and have a nice rest of the day. Bye for now.